Whee! Wow. So if you watched my first fan car video, you could see that I had some issues with the fan car itself. And probably like you, when something doesn't work the way I want it to, I kind of get obsessed with trying to come up with different solutions. So this all got me wondering if I could make a usable RC fan car, something completely different than my RC hypercar, which creates peak downforce at around 70 miles per hour. This would be a car with massive amounts of downforce, hopefully at 0 miles per hour. I'm going to actually take a step back and kind of test some different fans to actually measure their performance and see if any of them are even feasible for a project like this. One of the biggest problems I had with the fan dragster was the durability and accuracy of the fan components. Luckily for this video, I was able to partner with JLC 3DP, who helped 3D print the fans, the housings, and the filters. The fans were all printed in MJF nylon, which is strong, lightweight, and perfect for withstanding the high stress environment of fan operation. Also, the surface finish and accuracy is amazing on these fans. MJF is a great 3D printing process for having really strong and accurate parts. And this allowed me to have gaps between the fan and the housing of well under 0.5 millimeters. The housing and the cyclonic filters, which I'll talk about a little bit later here, were SLA 3D printed in a transparent resin, which will be great for actually seeing what is going on inside these filters. And then I have to mention, throughout all this, JLC's engineers were great helping me out during this entire process. The designs I came up with for these fans were really pushing the boundaries of what was possible with MJF, and they helped me develop some solutions so that the parts would actually come out right. And I just want to mention the prices were really good as well. I think when you think of online 3D printing, you think it's going to be expensive, but I think all of these fans were under $5 each in MJF nylon. And I even accidentally ordered one of the fans 3D printed in stainless steel, which was also not that expensive. But I'm convinced now that I need to find a project that has the requirement for 3D printed stainless steel, because the surface finish and accuracy are outstanding compared to any other 3D printing technology that I've worked with. So I've come up with 3 different prototype concept fans. The first up is a mixed flow fan. This is just a derivative of the fan used in my first fan dragster prototype. You can check out that video if you haven't already seen it. The main goal with this iteration was to make the fan as compact and lightweight as possible while still maintaining a reasonable flow rate and pressure ratio on the fan. Basically, I'm giving up some performance to try to make it fit into the frame of a 1/10 scale RC car. So if you actually look at this CAD drawing, you can see the air is drawn in here through the main inlet. It's pulled out and around this mixed flow fan. I believe it exits the fan at about 55 degrees and is forced out and around the motor housing itself and comes out this main outlet that surrounds this cooling outlet. And that's actually the coolest thing about this entire thing, is that I'm using a really small drone motor here, so it gets really hot, so I have to have really good cooling. So I've added a series of holes all around the motor here, and you can actually see this is where the air is actually drawn in. It'll draw in the boundary layer of the air as it's forced around the motor housing. And because there's a small nozzle at the outlet, we're going to end up with a nice low pressure region that's going to draw the air through the motor and force it out the back. And it also improves the performance a little bit. Now, to test the overall design and performance of the fans, and so that I could arrive at basically a number of blades and different styles of blades, I used AirShaper's online CFD platform. The simulations are very easy to set up. You can select the fan itself as a propeller, and set the RPM, and then you just run the simulation. When I was designing the mixed flow fan, a company named Sequre reached out to me asking if I wanted to try out one of their new brushless RC crawler motors and ESC combos. And that got me to thinking, well, I hadn't really tried any real world testing with a high flow axial fan or an EDF basically. And although axial fans aren't known for their high pressure ratios, as I talked about in my first video, they do flow a ton of air. And Sequoia's motor is a decent size at 36 millimeters by 25 millimeters. And the other cool part about it is it's still an 1800 kV motor, which means we can get some decent blade speeds and build a fairly large 64 millimeter EDF. What's also cool about this particular combo I found was that the ESC setup is really easy to do. It uses the Escape 32 firmware, which is one of the newest open source firmwares for ESCs. And it comes with what is basically an ESP32 dev board that plugs in as a programmer, which enables wireless firmware settings changes in the ESC. So it's extremely easy just to reprogram the ESC to actually be a drone motor rather than its normal use case, which is an RC crawler. The other cool thing is the motor is super smooth because the ESC uses a sinusoidal PWM so that it can operate at super slow speeds. In fact, I was actually so impressed with this combo that this may become the motor and ESC, well, for sure the ESC for the RC top speed car. The ESC supports 70 amps and it's super lightweight, and I think it's going to be perfect for an application like this. So if you're interested in picking one of these up, check out the link in the description below. And the last fan I have is a contra rotating fan. And this is a little bit more experimental. Once I figured out how to actually design a single axial fan, I couldn't resist going down the rabbit hole and trying out a contra rotating setup. And essentially this is like a two-stage compressor. The first fan generates a lot of flow and rotates in the clockwise direction. And the second fan takes that already compressed air and imparts even more kinetic energy to the flow and pushes it even harder out, and it rotates counterclockwise. So when you have these opposing fans, you basically have like a moving diffuser behind the first fan. This particular compressor has a first stage with 11 blades and a shallower angle of attack, and a second stage fan with 7 blades that rotates in that opposite direction, but at a much higher angle of attack that basically matches the angle of the air coming off the blades of that first stage. And what you want is to use prime numbers for the number of blades, because these are contra rotating fans and they are known to be obscenely loud. And when you use something like a prime number and the two numbers aren't divisible by each other, you should greatly cut down on that noise, although it's still an extremely loud fan, as we'll talk about later. I do want to call out one of the big issues though with contra rotating fans is that they're not easy to design and they often aren't terribly effective. There's a lot of complexity in getting the airflow right between the fans, but I wanted to try it out and see what kind of performance I could get. Now let's talk about filtration. In the first fan car, I had a lot of problems with debris, especially rocks getting sucked into the fan. While the nylon material I 3D printed the fan out of can handle small particles like sand, small rocks were a huge issue. They could jam up the fan or they could destroy the blades themselves. I had thought about just slapping a screen on the inlet, but based on other YouTubers who have done fan cars, these screens get clogged up very quickly, and I could see that being a really big issue. So that's when I got the idea to try to utilize something like a cyclonic separator filter. Cyclonic filters are great because they use centrifugal force to separate larger, heavier particles from the air, which is really the type of particles that I was trying to keep from going through the fan. And they're also self-cleaning, which means they won't clog up. And also they have lower losses because they're typically pre-spinning the air that's actually going into an already rotating fan. So that can actually help with your efficiency some. Now, ultimately, I have 3 different separators, all based on roughly the same design. The least aggressive separator just has some straight blades that actually go into the fan, so there's not actually any spinning action to the air at all going into the fan. It just has this large deflector in the center, usually called a core rod, that forces the particles out and away from the fan inlet so that we kind of have a baseline for what just a simple filtration system could be. The other two separator designs I have are variations on the actual twist angle of the blades themselves of the separator. I'm not actually able to simulate the weight of the individual particles themselves in CFD, but basically the more you twist the air and the more blades you have, and the longer the housing, the filter will basically filter out lighter and lighter particles and be more and more effective. I knew that I was already only wanting to filter out the heaviest of particles, and I wanted a relatively compact filter, so I knew that I was going to have to go with some fairly low twist angles, which both of these filters aren't very aggressive in terms of what you might see for like a dust separator or something like that. Now, the last piece of this whole filter here that I just want to kind of point out is the actual debris outlet. One of the ways of making a cyclonic separator more efficient is to actually pull a small amount of negative pressure on the debris outlet itself, somewhere in the neighborhood of 10 to 15%. And this just induces more spin, especially if you see my outlet here is a kind of offset to one side. And that will help to impart extra spin, as well as the debris themselves will actually naturally be cycling around the outside of the filter itself, and this helps to pull those debris out. So since this car will be moving forward most of the time, the debris outlet is actually located behind the fan inlet, just far enough away to prevent debris actually being reintroduced to the fan, but close enough that it's going to see enough low pressure that it's going to help encourage some of that debris to drop out the debris outlet, and hopefully the car will just keep rolling forward and the debris is going to just keep coming out the backside of the skirt itself. So the last piece I want to talk about is the actual skirt design itself, or the piece that actually seals the underside of the car. The reality is I actually designed an entire pan for a whole new RC car with a suspension loosely based off the RC hypercar, but it was a bit futile. It's a good enough draft of a pan design to try to actually test out what kind of performance we might be able to get from something in a 1/10 scale car, but it's got its issues. And I wanted to go ahead with using that for this particular test because I think it's going to be much more representative of a final design. If you saw my last video, I used a vortex sealing skirt, which did not actually contact the ground, but there was a 2 to 3 millimeter gap all the way around the skirt. And this was relatively effective in improving the overall static downforce created by the car, but it still had a lot of losses. And there was also problems when it would rub on the ground. If we could have a skirt that actually rolled along the ground and followed the contours of the ground, we could get a lot higher performance ultimately. And like I said in the last video, the McMurtry Spearling uses an active suspension and a really durable and expensive metal ceramic matrix seal that slides on the ground. It's really cool tech, but for this I wanted to try a design, again, that just uses some rollers and casters to keep the skirt just 1 millimeter off of the ground. Because of the suction, the skirt will naturally tend to be sucked to the ground, but the wheels themselves will allow it to roll more easily and hopefully follow the contours of the ground. The last item before we actually get into testing here is I want to talk about the shape of the skirt, or that underfloor itself. I blatantly ripped this off from the Red Bull X 2014 fan car that was designed for Gran Turismo. And because of AirShaper and their awesome CFD simulations, I now know why the Red Bull car was designed, their floor that way basically. And that's because when a fan car is moving forward, a huge amount of high pressure air is being forced under the front of the skirt of the underfloor, which makes a lot of sense. And the faster you go, the more downforce you will lose. So if you actually look at the Red Bull design, you have this nice point here at the front where it's forcing air to go out and around the seal rather than getting forced under the seal itself. And then it comes to a point at the back, which actually lowers the drag a lot more, so the air will follow it all the way around. And because you're drawing some air no matter what under that seal, you're going to be drawing off that boundary layer, and the air is going to stay nicely attached all the way around the seal and hopefully come out the back. There's no perfect solution, but I think this is much better than the solution I came up with for the fan dragster. It does have less actual surface area, but I think that that trade-off in performance will be worth it. So let's talk about the actual test setup here. It's pretty straightforward. I have some screws in the bottom of the pan that hold it at the ideal ride height of the car, basically with downforce. To test the fan performance and losses from the filters, I've created this quick test setup. So this whiteboard here weighs exactly 1 kilogram, and I will have it sitting on top of a scale that has been tared to 0 grams with the board sitting on it. The 1 kilogram is higher than I expect the fans to be able to generate in suction force. So the plan is to actually put the car on top of the board. I'll turn the fan on, and then I will lift the pan itself a few millimeters. The skirt will still be blocking the air. Basically, this will be in the movement zone of the skirt. And I will be able to see how much weight is actually being taken off of the scale. So then, knowing the weight's taken off, I can actually compare the relative performance of each of those fans in the actual real world. And then I can also divide that by the surface area of the floor so that I can figure out the relative pressure differentials of the different fans. And before I go into this, I'm just going to note I live at 7,000 foot elevation, so I have lower air pressure, and this will affect performance anywhere from 20 to 25%. Here comes the big scary one. Lots of power. This thing has a lot of torque. Okay, contra rotating fans, test 1. Very, very scary. So this chart shows the test results from the different fans, and they're kind of how I expected them to be. A mixed flow fan performed the best, followed by the single axial fan, and then at the lowest was the contra rotating fans. The contra rotating fans did not perform as well as they sounded. The sound was absolutely insane. It was a very weird noise and absolutely the loudest thing I've ever built. Even with earplugs, it was uncomfortably loud, but clearly I didn't get the design right. The axial fan, the single stage one, performed fairly well, but it's still not up to snuff compared to the mixed flow fan itself. And this is just because the mixed flow fan just has so much higher of a pressure ratio potential. Basically, it has the ability to generate a larger difference between the inlet and the outlet pressures than an axial fan will ever be able to do. It's still a lot lower performance than I was hoping for. It's only about a pound of downforce, or about 400 and some odd grams. Now, the original fan dragster I made previously has between 30 and 35% more surface area on the underfloor. So if we compensate for that surface area, you can see the newest version of the mixed flow fan has performance relatively close to that of the original fan, despite being quite a bit smaller in overall diameter. Although you can see the larger version 1 fan seems to perform much better at lower speed, which is expected. The larger diameter is going to give you more expansion, particularly at low speeds. And I think honestly that the version 2 fan needs to have a higher battery voltage. It's around 20,000 RPM right now on a 3S battery. And realistically, rough simulations are showing somewhere around 35,000 to 40,000 is the sweet spot for that fan generating its maximum pressure ratio. So moving on to the actual cyclonic filters themselves. Since the mixed flow fan was the best performing fan and it's the easiest to configure for me, I went ahead and tested the 3 different filter designs with that fan to see how they actually affected the downforce being generated. We get some interesting results with this. First, the filter with no twist angle at all performed the worst, except for a tiny bump in performance at very low throttle. Then we see that the most aggressively twisted filter, what I'm calling the spicy filter, with I think 72 degrees of overall twist angle, performed the best. Honestly, I thought the spicy filter would just be too aggressive and was going to cause a performance drop. But basically what's happening here is the filter is actually helping to pre-spin the air as it's coming into the fan. And this reduces the energy the fan has to spend accelerating the air. It reduces some of the air separations inside the fan, and it can actually improve the overall fan's operating range. As you can see, even at 50% throttle, the more aggressive spin was generating more downforce. The other cool thing about having a more aggressive twist angle is that it actually will improve the filtration that the filter can provide, because it's going to be spinning the particles harder in the filter. I mean, this graph tells me that despite my intuition, I may need to try an even more aggressive twist angle for the separator and see where this increased performance due to twisting the air before it goes in the fan, where this increased performance plateaus at. So now for the fun part, let's try and destroy some fans. So to test the 3 different filter configurations, I'll be using the mixed flow fan since it performs the best, and I have 2 different debris substitutes. For fine particles like sand, I will be using sugar, and to test out the fan's performance with small rocks, I will be using these airsoft BBs, which have a very similar shape and size and density to the rocks that I encountered that the fan was able to easily pick up and ingest. I'm going to start with the sugar first, since this has the lowest likelihood of destroying the fan. So you can see a couple of things in these videos. First off, the debris outlet is working well, and there's a nice little trail of filtered sugar that's left behind as the car is pushed forward. Secondly, a lot of the sugar just passes through the fan itself, particularly with zero twist angle. Most of it just goes right through, and with the mild twist angle, it's kind of in the middle. But in all cases, it appears that the larger grains of sand are being left behind as they're being filtered out and dropped out through the debris outlet, and the finer grains are going out the discharge. Kind of what I was expecting. It's nice to know that some of the larger particles of sand would be filtered out, but again, it's not a deal breaker one way or the other. Moving on to the airsoft BBs. These are just a little bit too big to fit under the gap of the skirt. Where I typically see rocks actually getting sucked up into these fan cars is when they go over cracks in the pavement, which will be full of rocks. So I'm going to go ahead and place all of the airsoft BBs under the skirt itself, and we will see how many of these get jammed into the fan itself. Here you can really see the Cyclonics in action. With the zero twist filter, the BBs are just bouncing back and forth. Sometimes they hit the fan blades and they bounce out, and sometimes they shoot out the back of the fan. I did have one get jammed in the fan, which have burnt out the ESC almost instantly. But it's clear when you actually look at something like even the mild or the spicy filter that the BBs are spinning around the filter housing at a pretty good rate, and you can see them drop out and be deposited out the debris outlet. I tried really hard to try to get a BB sucked into the fan, but with a spicy filter in particular, I didn't even hear a BB bounce off the fan, not even once. I'm still not certain that a fan car is the best way to go. The added weight of the fan, filter, and skirt for the lightest versions of everything are about 120 grams, and you would gain something like 300 grams or so of downforce at zero velocity, which isn't insignificant, particularly at low speeds. If this was at sea level, this might even be closer to 360, 380 grams of downforce. If we're really careful with weight designing a 1/10 scale car, you're looking in the neighborhood of 1.2 kilograms fully loaded with the battery. So this would provide at least a 25% increase in traction. I don't currently have a 4S battery, and I'd like to test the mixed flow fan out at a higher RPM. I think that we may see a significant boost at higher RPM. You can see how big of a jump just going from 50% throttle to 100% throttle has on these fans. These fans have a fairly narrow operating sweet spot, I guess you would call it, where they're efficient and generate good pressure. But let me know in the comments if you think there's something I'm missing out there, you want me to try something else, or if you guys even think it's worth trying to develop a RC car around having powered downforce. I think I'm kind of jaded by the RC hypercar that generates like 4+ kilograms of downforce at 70 miles per hour. So just to close this out, I want to thank everyone that helped out with this video. Special thanks to JLC 3DP for these beautiful 3D prints that I was able to use to demonstrate how all these different fans worked. And I want to thank AirShaper for providing the CFD services so that I could design and test these different fans before I just printed out 100 different fans. And check out Sequre if you're in the market for a compact and powerful RC crawler motor and ESC setup. And I have the links to all three of these guys down below in the description. So until next time, stay safe out there.